We're going to continue to look at our partial derivatives and the fact that the total change in voltage as we move off of a position in space can be given by seeing how much change you have in the x direction and then letting the proportionality factor dv dx give us the number, that factor that goes along with the change in x to get the total change in voltage. And then similarly with y and with z, those differential changes have their proportionality factors that give us the total, ultimately give us the total change in the voltage. Now, the first thing we need to do to better understand the mathematics that's used with this type of calculation is that the dot product of this bracketed term with this bracketed term gives us Roman numeral 1. So Roman numeral 1 here and Roman numeral 1 here, those two equations are the same. So let's see why that's the case. If we take the first term here and we distribute the dot product through, well, as soon as we dot x hat with y hat or z hat, we lose those terms. So when we take the dot product, we are left scalar, right? So we have x hat, cosine of 0 is 1. We are left with this bracketed term. And we'll do the same thing with the y and with the z. So please take a moment, pause the video if you have to convince yourself that this equation and this dot product really are mathematically the same thing. Okay. All the mathematicians have done to introduce what is called the gradient operator or del operator is to let the notation, right, this bracketed term equal this symbol, which they call the del operator. So please make sure you get in your notes if you go back and look at this at some point that the del operator takes the derivative of a scalar function, in our case the voltage, with respect to individual directions and then assigns x hat, y hat, and z hat to those directions. Hopefully that makes sense. Well, to understand this defined gradient vector, so that is the gradient vector, so that's what mathematicians are referring to. To understand the gradient vector, you really need to understand that Roman numeral 1 equation and the fact that doing all these partial derivatives with x, assigning the values to it for our gradient vector, and then taking that dot product with respect to whatever change in space you are undergoing, so that represents your dr, right? So that's the dr here, gives us the total differential change in voltage dV. Well, that total differential change in voltage dV only has one maximum value, right? dV can only be maximized by going in one direction, and by understanding the dot product, so the dot product will be a maximum when cosine of theta equals 0, 1 gives us a maximum. That means we know the dr vector and the gradient vector line up when we are going to get a maximum change in voltage. That means that and this is the most important part in terms of understanding why it is that the gradient vector, this gradient v, has to be in the direction of maximum increase. That del vector v, the gradient of v, has to be in the direction of maximum increase because when we take the dot product with any dr, right, we know we get a maximum change in voltage. Like this green guy over here, that's the most important part to us. The maximum change in voltage happens when the dr lines up with the dV, or the del V. So that del V is actually fixed. That's what this is showing us. The del V has to be fixed in space, giving us the maximum direction of the voltage, which has to be perpendicular to the voltage because it has to be parallel to the dr. So I realize there's a lot going on there, and we don't need the mathematics of the gradient and the del operator for our class, but if you go on in physics and engineering, you will be coming across this gradient vector. Hopefully this will help you out in at least having seen it initially here. So the max dV, and I should put here along dr, happens at theta equals 0. So that means that max dV, that's our green one, right? So that max dV is that. That's what locks in our gradient of the voltage and the dr pointing in the same direction, and the fact that the gradient, so this is our gradient of the voltage, must point in the max dV, and here we have it. The physicists just take that gradient and invent the electric field vector. Kind of cool. And in physics, what's further, we're not interested in the maximum direction for the voltage. We're interested in the maximum decrease because we want those positive Q's to go from high voltage to low voltage. So the physicists throw in the negative here, not the mathematicians. And we will see on our next page of notes the mathematical technicality of taking the partial derivatives that you are responsible for. You will need to be able to generate the electric field equation if you're given a voltage expression in 3 dimensions, and we'll see that on our next page of notes.